So in this chapter we'll be looking at the Lewis model for chemical bonding. I just think it's kind of interesting. This structure that's shown on the left, its name is tetranitroxycarbon, was actually created in an elementary school classroom when a chemist came in and handed kids a bunch of molecules, and one of the little girls actually put this together and says, "Does this exist?" And he looked at it and goes, "I don't know. It seems like it follows the rules." And so he went and took it to a friend of his who's a professor, I believe at Humboldt, and he did some calculations on it. He sure enough verified that, yeah, this is a molecule that could exist, but nothing in this class of compounds has ever been made. And so this little girl got herself a publication. I think she's probably about 10 years old, so that was pretty neat. Anyways, the strength of the Lewis model is its simplicity, and it allows us to predict a lot of different chemical structures and what they will look like. And I mean, the proof is in the pudding when this little girl came up and invented this whole new class of compounds just by playing with the models. So the basic premise of the Lewis model is that we can predict the bonding based on valence electrons. And we'll learn about a Lewis dot structure where we just draw the electrons as dots around each element, the valence electrons around the dots of each element, and we can use those to predict how they will bond with each other. Lewis structures, as I mentioned, allow us to predict a lot of different properties of the molecules, including their stability and what they might look like. So let's review real quickly what the forces are like between atoms that would be bonded. So the basic components of forces of attraction between atoms would come from the nuclei, which have positive charges, and the electrons, which have negative charges. Now, there'll be, according to Coulomb's law, right, opposites attract, and that there will be a force of attraction between the nucleus and the electrons. On the other hand, the electrons themselves, because they have similar or like charges, and the protons themselves, the nuclei, right, have like charges, so there will be repulsive forces that occur between those sort of components of a chemical bond. So you might ask yourself a question like, why do bonds even form? Because the nuclei repel each other and the electrons repel each other, right? And we'll talk about that. But in essence, bonds form because when the atoms are bonded, they're lower in energy than when they're not bonded, right? So bonds form when the bonded atoms are lower in potential energy than the atoms, the separate atoms, right, that formed the bonds or formed them, right? Now, we have to think about lower potential energy, but overall, it's a situation of more stability. So we've run across a situation like this before when we talked about the Bohr model for the atom. And the Bohr model for the atom, we had ground state electrons. If you remember, we had for n equals 1, this was minus RH. And then for n equals 2, it was minus RH over 4. And then it became over 9. And remember, these lines get closer and closer and closer together. And if you remember, I believe it was a homework question that brought it up. But eventually what you do, when n is equal to infinity, in essence, you reach a situation of potential energy that's equal to 0. So this is actually higher in energy, this infinite energy level, or even minus RH over 4, is higher in energy than minus RH. So in essence, electrons go to the ground state simply because this is the lowest energy state that they can get to. So let's think about this potential energy as we think about how two hydrogen atoms might form a bond. So like the Bohr model, when the two hydrogen atoms are infinitely far apart, they have 0 attraction towards each other. So in other words, we do have, just like in the Bohr model, a zero potential energy line. So I often sort of equate this as how I met my wife. So I didn't actually know she existed when I was in California at UC Santa Cruz, and she was at Iowa State University. So in essence, when we were infinitely far apart, now we're not infinitely far apart, right? I mean, there was a chance that I could know her, but for all practical purposes, she was infinity away from me. There was no attraction there because I didn't know she existed. In a sense, then, I have a hydrogen atom way out here, and I have another hydrogen atom way out here, and I'll draw these as little electron clouds, right? And there's no force of attraction. So that's what this zero line represents. Now this equation is actually Coulomb's law, and I forgot to put a minus sign in there. So right here we should have a minus sign. It didn't mean to zoom, it just did it all on its own. A negative sign there. Now Q1 and Q2, well actually there isn't a negative sign, my bad. Q1 is perhaps positive and Q2 could be negative, but that would represent the electrons of one atom versus the nucleus of the other atom, and that forms potential energy that's attractive. Now as R gets smaller, right, this term gets more and more negative because one of the charges is negative. The result is as two get closer together, you have a potential energy curve that looks something like this. And again, if there were no restrictions on how close they could get, they would get infinitely close together, or they would form one unit, right? Now, on the other hand, if you think about when two objects are really too close, right? Two atoms are really too close, then what happens is these two, while they were attractive at some point, these two become repulsive and these two become repulsive. So at a distance it looks really good, but up close it gets ugly, right? So we have attractive forces coming down, but then we have repulsive forces that get stronger as you get closer, and it looks something like this. And in essence, if R went to zero, it would be infinitely repulsive, okay? And again, the analogy of the relationship is, right, as you get to know somebody, often they're really, really attractive to you, and you think you can get infinitely close. And then on the other hand, when you get infinitely close, you sometimes find out they're infinitely repulsive, and you try to get out of the relationship. So, but here's what happens. These terms combine. So this is for the like charges, so two positives or two negatives. So this would be Q1 is positive, Q2 is positive, or Q1 is negative, and Q2 is negative, like that. So those are situations that we have that would create an upward potential energy curve. What atoms really do, though, is they take and combine these two curves, and what you get is a curve that looks something like that. Okay, so there is an energy minimum down here, but it begins to rise up. Now, you notice I've plotted radius down here, and this is potential energy over here from Coulomb's law in a conceptual sense. What happens is when you reach the bottom of this well, right, as you get closer, then you begin to crawl out of the well, basically. This is when you find out somebody uses their car keys to clean their ears, and then, that kind of stuff. Whatever you can think of that's gross. So here's the deal. This is the bond length. Okay, I marked it down here on the video, but this length is the bond length. This energy is the bond energy. That's how strong the two are bonded together. So there's a combination, right? So from a distance, they're always going to be somewhat attractive. As they get closer and then the like charges get really close to each other, then they become repulsive. And then when you sort of synthesize those two and you make a single curve out of them, what you find out is there's a minimum down here. And this is where atoms like to sit when they're bonded. They have a bond length. And real atoms just like real people in their relationships, the bottom of this well oscillates back and forth. They're too close, too far apart, too close, too far apart, but ultimately they oscillate around a particular bond length. And we can actually measure that. We can use spectroscopy again to measure the vibrations of that bond.